Hey everybody. So, yep, I'm Sylvan Clebsch. I do indeed work for the Borg at Microsoft Research in Cambridge. And I'm a language designer. And the reason I know I'm a language designer is that people at work make fun of me for being a language designer. And that's the quickest way to find out what it is that your job consists of. So, roughly speaking, I'm going to talk about semantics, and specifically, I'm going to get into small step operational semantics. But the first thing I want to find out is if anybody knows how a computer works. Anyone? Hands up if you know how a computer works. All right. I think I'm not totally sure all of you know what I mean when I say, how does a computer work? So, hands up if you understand the micro-op decoding phase in an x86. All right. Hands up if you have the Intel internal documentation about micro-op decoding in an x86. Right. Pipelining, speculative execution, branch prediction, register renaming. Everyone's pretty comfortable with that. How about memory? Everyone understand how cache coherency works? Prefetching. Do you know how the hardware prefetcher works? Do you know how an x86 makes hardware prefetching decisions? Now we get exciting, because it turns out when you get to branch prediction and hardware prefetching decisions, it turns out that that's actually done with machine learning now on the fly. So if you think that's understandable, that's a different conversation. Virtual to physical address translation, content addressable memory, pretty comfortable with that. Yeah, so there's not a lot of hands here. That's good. I/O, people are comfortable with the full PCIe architecture, programmed I/O, direct memory access, RDMA. All right, good. Excellent, because it's a trick question. These are exactly the details that a programming language should not surface. And the more we surface these kinds of details, the more we trap ourselves. So generally speaking, this is the stuff that we tend to call microarchitecture. Really, microarchitecture only really refers to CPUs. But that distinction is sometimes getting blurred these days, and people sometimes use it to mean the crap that we don't actually expose. So the stuff we do expose, roughly speaking, we like to call the architecture. Again, that's not totally true. And it is true that systems programmers and compilers for systems languages need to understand how this stuff works, because that's how you get efficient code. Now, admittedly, the less a systems programmer has to understand this stuff, the better off we all are. And that means moving magic into the compiler. But of course, there's problems with moving magic into the compiler. But that's sort of a separate subject. What I want to talk about is, what does the systems language itself understand? Which is different. That's not what the compiled code understands, right? That's what the language itself understands. What does the language interact with? And that's, in my opinion, an abstract machine. And an abstract machine, hands up if you're comfortable with the term abstract machine. All right, that's much larger than usual. I like that. So roughly speaking, we're talking about step-by-step execution, right? And yeah, we're going to omit details, we're going to gloss over stuff, but in the interest of having a more general model that can be specifically applied. And again, so simplified or detailed, implicit or explicit, like there's many ways to talk about abstract machines. Turing machines, simple, explicit, abstract machine, fantastic, nice and easy to reason about. The CLR, the JVM, a little bit more detailed, but still explicit abstract machines. One of the ways I like to think about process virtual machines, actually, is that they are executable abstract machines. It's kind of fun. And then, of course, C operates over a detailed and implicit abstract machine that nobody can define. And roughly speaking, yes, David Chisnell is right. Roughly speaking, we still pretend it's a PDP-11, and it isn't. So a programming language then describes the steps that we take on the abstract machine. And that's true even for things that aren't imperative languages. A lot of times we start talking about step-by-step execution, and people say, OK, this is a model for C. This is a model for imperative languages, structured code, this kind of approach. But that's not really true. Roughly speaking, the Warren abstract machine is still how we do logic programming, roughly speaking. SecD is still the foundation for strict functional languages, and arguably even for lazy functional foundations in a very foundational way. It's a much older model. It's a 60s model. There's clearly a lot of work that's been done since then. But abstract machines drive execution no matter what the paradigm is. And it's semantics, operational semantics, well, lots of semantics, but I'll get to that, that describe that interface. The semantics of the language describe how the language talks to the abstract machine. And there are many ways to do this. The most popular by far is to write an interpreter or compiler with no specification. The other approaches are things like axiomatic semantics, denotational semantics, operational semantics. They're all very useful. They all have their purpose. I'm going to concentrate on operational semantics. That's just my personal preference. That's not a judgment on which of these is a good approach. But there you go. So, operational semantics. Roughly speaking, there's two kinds of operational semantics. Really, that's not true. There are more. But if you think of it as, there are big step operational semantics, which say, what's the final result? I want to be able to go all the way through the execution of the program and have some understanding of what the end result is. Big step works great. It's really intuitive to write. There's a really nice way to reason about it. When you describe it to people, you get it really quickly. Small step operational semantics describes each transition individually as a separate inference rule, where each inference rule can be applied non-deterministically, but each inference rule is atomic. Not atomic in the sense of the CPU, like Tony was talking about earlier, although there are atomic operations expressed this way, but atomic in the sense of the abstract machine is not interruptible at that point. So a lot of things are atomic that we don't usually think of as atomic operations. For example, reading a 32-bit value on an x86 is an atomic operation. We don't think of it that way because there's an asynchronization problem, but it's atomic in the operational semantics sense. One of the things that is very attractive about small step operational semantics is that you can very easily express concurrency. That level of detail over each inference rule and the ability to non-deterministically select the next inference rule gets you the ability to encode concurrency and actually parallelism in your inference rules. That's really useful. That's why I tend to reach for small step operational semantics personally. There are many approaches. Each has their purpose. That's what I tend to reach for. So, why am I not talking about starting with syntax? So, this actually goes into a bunch of the stuff that Joe was talking about. I say many programming languages design start with syntax. Arguably most, I don't know, but certainly many. There are lots of reasons for that. Probably the most common is that there was no attempt to think about the operational semantics at all. Or that the semantics was assumed. So in the case of C, it's not that nobody thought about it, it's just it was assumed that the only model of execution that there ever would be a PDP-11. In other cases, it was less clear why the decision was made, but there you go. In some cases, it's because there is an existing semantics that is exactly the semantics that people want. That's what's being targeted, and it's on purpose. So one of my personal favorite languages, F#, was done in exactly this way. The entire purpose was to bring functional first programming to the CLR, to .NET. So the semantics was a given. The same goes for Scala. The same goes for TypeScript, another hugely successful language, right? So these are important and extremely useful approaches. This is in no way about, oh, you shouldn't design a language like that. Of course people should design languages like that. Absolutely they should. But not always, right? Sure, it lets you do this stuff about focusing on the user interface part. All programming languages are user interfaces. And there's all these really important points that you get to address when you're working from the user down. But there are other things that you might want to do. So why would you start with semantics, given that it's sort of by definition going to be harder? One of the reasons is because you have an entirely new execution environment. So GPUs, FPGAs, you really don't have a choice at that point. If you don't define the abstract machine you're going to execute over when you go down this route, you're going to end up with garbage. Another is new communication mechanisms, distributed programming, distributed transactions. That generally means you probably want to start with a nicely fleshed out semantics before you move on. New runtime features. Interestingly, I think garbage collection is one of these. A lot of people say that garbage collection should be invisible to the semantics. but I think there's some interesting power in making the garbage collection explicitly visible to the semantics. For example, you can start talking about the compiler understanding safe points because they're expressed in the operational semantics. That's pretty fun. Hot code loading is one of my favorites for this, and I don't just mean dynamic loading here. I mean actually replacing a set of code that's running in your program live. Erlang does that. Interestingly, there's some C++ that does that in a certain place. That's powerful. If that's not expressed in your semantics, that's a really easy one to get horrifyingly wrong. Another one is new deployment requirements, cross-platform, embedded devices. People are like, oh, it's just a smaller machine. It's not just a smaller machine. It has a different cost model, right? It has a different set of hard limits. It's one thing to say we consider the operational semantics over infinite memory. It's another thing to deploy code, right? New application domains. So machine learning and reproducible science are driving a lot of this right now, as well they should. It's a huge area. But evolving concrete machines, that's important too. And funnily enough, Mario talked about some of this with non-volatile memory. I think this is also important with non-uniform memory. So non-uniform memory already starts getting in your way on a multi-socket machine, where you like a 4-socket machine, and the way NUMA nodes are done over that. But it really gets exciting when you start talking about rack scale machines, where you're using RDMA to treat the memory over 32 machines as a single addressable space. That is a place where you might want to start with your semantics. So there's some other stuff you can do. This is sort of the part 2. What if it's a much softer thing? What if you're dealing with hardware that isn't really massively different? Well, let's talk about safety. So safe languages mitigate security flaws, right? That's the whole point. We're not here to do safe languages in general because safety is nice. We're doing it because the lack of safety is expensive. So mitigations for languages that aren't designed for those mitigations are sometimes possible, and they are sometimes not cripplingly expensive. Those two things don't necessarily hold true at the same time or at all. So one thing you can do is start by designing a safe semantics, where safe is definitely relative to a threat model. Are people comfortable with the term threat model? Done threat modeling? A little bit. So I'm going to actually expand on that a little bit then, because it's worth understanding, I hope. And also, please feel free to ask questions and stuff. A threat model is, roughly speaking, the surface that you are, the attack surface that you're intending to protect against. If it didn't show up in your threat model, the chances are you're still vulnerable to it, right? Something not in your threat model doesn't mean that it's okay. It means it's almost certainly very, very bad indeed. So for example, if you're a major CPU manufacturer and you have a threat model about process isolation and your MMU and things like that, and you introduce a new feature to improve performance by letting you execute both branches of an if statement at once and then go back and decide which one was right, this may not have been in your threat model. And you may discover, about 20 years later, that your processor design was slightly less secure than you originally intended. So, that said, if you do design a safe semantics, anything that runs on top of that safe semantics is safe, until we figure out what we left out of the threat model, right? But until that point, that's a nice motivation too. This is the approach to safe systems programming languages that says that stuff that got in the swimming pool, you can't take it back out again. So you can't fix a legacy language when it comes to safety concerns. Is this true? I don't know. Static analysis goes a long way. There are a lot of other approaches. This is one approach. But it's going to be harder. I sort of said this before, but roughly speaking, you're going to have to define the abstract machine. You need to define the semantics. You're still going to have the syntax. You're still going to have to bike shed like crazy on the syntax. You'll need to target a new and untested semantics when you write your compiler. Is it worth it? Sometimes. But let's go down this route. Let's build a semantics. So if this is stuff you already know, just say, let's go faster, this is easy. If it's not, and we want to go slower, and we want to get really specific about stuff, speak up. If there's other stuff you want to talk about, if you want to express things in a different way, if you want to talk about other formulations, please, please, please say so. So, First, before I start showing any semantics, I'm going to talk about a few cheats when you write up your semantics. First of all, it's really important that your operational semantics is not a syntax-driven interpreter. And a lot of times when people go to write an operational semantics, they take the syntax of the language and they say, okay, given that syntactic construction, I need an inference rule that does exactly that. That's not a great plan. Syntax-driven interpreters can get you into a lot of trouble. Instead, let's go for an intermediate representation where you have confidence that your language can be expressed in that IR, and that IR can help out the way that you structure your semantics. So there are lots of things like that, lots and lots of things. Single static assignment, expression holes, which funnily enough Arjun covered earlier, continuation passing style, kind of close to what Arjun was talking about, and anormal form. So is anyone familiar with anormal form? Oh, quite a few. Excellent. Good. So roughly speaking, we're going to let bind non-trivial expressions. That's for the people on the functional side of the programming language community. Or we can say we're going to use a crap ton of local variables. That's people for the imperative side of the universe. It's the same thing. Essentially what we're going to say is anything non-trivial has to be bound to a name such that when you want the result of the non-trivial expression, you're going to use the name of the result. Okay. Names like X. So, is everybody comfortable with this slide? Who's not comfortable with this slide? Please say so, because we're going to get in a lot of trouble if you're not comfortable with this slide, and I can explain it. Fantastic. Totally reasonable. What we're saying here is that X, Y, and Z are local IDs. We're not saying that those are all the local IDs. They happen to be the local IDs that we're going to use to express the semantics. Again, it's not a syntax-driven interpreter. It's not that these are all the local IDs in the universe. It's that this is how we're going to express the semantics. And we're going to say that phi is a frame. And what is a frame? A frame is a mapping of local IDs to values, where v is a value. And right now, we're just going to say all of the values are integers, because clearly that's all anybody ever needs, because BCPL. So if we have that, let's talk about inference rules. If this holds, then we're allowed to do this. It is not, we must do this. It is merely we are allowed to do this. This is one of the rules that we may select. Is that okay? Everybody all right? Fantastic. So this is going to be the shape of the semantics that we're going to show here. We're going to build a little tiny semantics. This is going to be the shape of it. We're going to say if we have a frame and we have an expression, then after evaluation, we're going to have a frame and either an expression or a value. Does that make sense? And we can write it nice and compactly, like the phi e goes to some other phi and either an e or a v. And actually, that should be e prime. It's not necessarily the same e. Okay? Yeah.
And we also have something like, a heap.
No, not right now.
Like
there's many ways to talk about programming languages that have no heap. Forth is an interesting way to talk about programming languages that have no heap. You decide what you want to decide. But right now, we're going to talk about frames. We're not even going to talk about stacks right now. Yeah?
Just to clarify, the stuff on the right is
I'm sorry?
How is the stuff on the right of squiggly arrow prime stacks? Is it P prime, comma P, or V, or is it?
I apologize. Yes. So in this case, the or is binding more strongly than the comma. It's an E or a V along with a frame. Yeah. So this is our first rule. All right. Who wants to tell me what this rule does? Come on. We just walked through the whole shape of the semantics. Someone should be able to tell me what this rule does. Yeah.
So if we have a variable x that is in the domain of the current frame, which means that there is some function that will give us, so there is this frame phi that will give us a value for x.
Absolutely.
Then we can say that in the frame phi, the vector x will evaluate to the same frame and to the value that phi gives us for x.
Fantastic. So this is local variable reading. That's perfect reading. This means we're allowed to read local variables. Excellent. Fantastic. Operational semantics is easy, see? The next step is this one. It's relatively straightforward too. We have a little bit more notation here, but it's nice and easy. We have some frame. We have x. We're assigning x some value. This is initialization. And if we do that, then we're going to have a new frame such that x maps to this value. And now x is in the domain, and we can read back the value that we assigned, and everything's fine. Nice, easy, simple. in this particular case, we're going to say that we're going to put that value as the result of this expression. In a normal form, that's not really all that helpful, but later on we'll see that if we want to talk about termination, that's going to get us termination. So, what does this do? We had the first one, we had the second one. Yeah.
Axis is a variable, and obtains the value it contains.
Okay, but what does it do with it? Because that's what the first rule did, right? It read x. What does this do? This is a separate syntactic form. Yeah, so specifically, it's a specific kind of assignment, which is a copy. We're copying the value of y into x. That's super important in anormal form because you're going to let bind everything. You need this in order to perform most of your operations. But that reads really nicely, right? Is anyone uncomfortable with this? Please speak up if you're uncomfortable. Fantastic. Yeah.
Will you briefly show the previous slide?
Sorry?
Will you show the previous slide again?
Absolutely.
Yeah, okay. Thank you.
Excellent. So the next thing we're going to do is we're going to talk about an operator. This really is a placeholder slide in a funny way. This is, you can expand this really easy to any kind of operator. In this particular case, we're going to do addition. It reads a little bit longer because we're going to have to say that x and y do both in fact exist. Otherwise, we're not allowed to read them. We're going to perform a mathematical operator on the value. We're going to assign it to z. Everything's fine. Relatively speaking, easy. Yeah.
So if you would not have postulated that all values are integers,
yes,
I would already get a headache at this point.
Yeah.
Because we're doing addition on, in this case, integers, but...
Yeah. So once you start getting into the idea that not all values are integers, you start adding more preconditions. So one of the things you might say is that they have to exist and 5x, the value that's held in 5x has to be an integer, right? And in some sense, we're saying then you're pattern matching on type, you're encoding that in the semantics, and you can make the right decision. The other way around this is to say, no, that's the wrong approach entirely. You want specific functions that do addition on integers, and you encode them that way. Really, either is fine. I prefer the second one, actually, rather than this, because then anytime you're encoding complex things like pattern matching on type into the semantics, you're saying that that's how it must work. And we don't usually want to say how it must work, but rather how it should work, how it does work, if that makes any sense. OK. Fantastic. Anyone want to try these? OK, I'll give you a clue. Sometimes we want to do more than one thing, and that's what we get out of this. So this is a sequence of expressions. And the first one says, given some sequence of expressions, E1 and E2, if E1 were to evaluate to a new frame and some additional expression, which is not something we've seen yet, we've seen things evaluating to values, then it would be fine to say that the next step in the operation is to operate over that modified frame with E3 followed by E2. This is an extremely powerful rule. It's this kind of rule that gets you this sort of interruptibility of a small step operational semantics. This is what gets you the ability to say, even if we haven't finished some complex expression, we can take a single step in the evaluation of that expression and then non-deterministically select what to do next. Now, in the case of single-threaded executions, it's not maybe all that exciting. But when we start talking about multi-threaded execution, this is the foundation of how we do it. This is how we express it. Now, this one is the corollary to this that says, what if E1 is actually, in some sense, finished as an expression? It's evaluated all the way to a value and we're done. Great, now we can evaluate E2. Now it's time to move on. So between these two, we get to drive to the conclusion of E1, but we get to do it in an interruptible, non-atomic manner. Does that make sense? All right, fantastic. So how about this? Anyone want to have a go at this? This leverages the rule that we had just before, particularly that top one. All right, so we're just going to start by saying it's if x, right? So this is clearly a conditional. And x is going to have to be in the domain. Otherwise, it's an invalid rule. This is undefined behavior. And this is the particular case where if we do look up x, it's non-zero. Because remember, we only have integers. There's no Boolean. So we're just going to pretend we're C and that only the integer 0 is false. In that particular case, we are going to rewrite this to be 5 followed by E1, right? The conditional branch, not the non-conditional branch. What are we going to do with E2? Drop it, forget it, doesn't matter, never happened. Okay, so this is the rule that lets us do partial execution here, right? We get an expression out of it, not a value out of it, and we're going to evaluate that expression next. So we've, in some sense, extracted E1 out of this conditional as the thing that we are going to select to do next. Okay? What does that do? Come on. Yeah, go for it.
Well, that's for the case when x evaluates to 0, because in that case we have to evaluate the else statement.
That's right. Exactly. So we drop E1 and evaluate E2. Fantastic. So that takes 2 rules to express the whole thing. Now, we're not doing anything crazy and complicated in our preconditions. Yeah?
So I guess is this probably the place where if there were an operational semantics for C, that's where it would mess up with the all right condition stuff?
No, so that's extremely good question. So because this doesn't cover micro-architectural details, right? This is architectural details. This operational semantics explicitly does not say that the CPU should or should not do speculative execution. It says, regardless of whether it does or not, retired instructions will take this form, right? Yeah?
Would speculative execution be similar to saying that we could have the same type of rule that instead of the condition that we had before was sequence, but inside the if? Like
You mean like this rule?
Yeah.
The best questions are the one for which the answer is on the next slide. Yes, exactly. Yeah?
The instruction that retire to where?
I'm sorry?
The instruction that retire.
Sorry. So is everyone familiar with the term retired instruction? Excellent. So just because an instruction is handled by the CPU, in some sense it goes through decoding, it runs through, it calculates the result, it pollutes your cache, it exposes you to side channel attacks, doesn't mean that it was an actual instruction. The instructions that are speculatively executed and then shown post hoc to have been correct and then are materialized such that the store buffer will actually go to the store, is roughly speaking how to think about it. Those are called retired instructions. And a lot of times when you're doing really fine-grained performance tuning on an x86, for example, you're looking to maximize your retired instructions per cycle. So theoretically, with simple mathematical instructions, bitwise stuff, addition, things like that, you should be able to get to, roughly speaking, 4 instructions per cycle. Real programs, if they're really good, get to about 2 instructions per cycle. Most programs get to 1 instruction per cycle. Yeah.
It may be useful to use the terminology, or at least draw the analogy with the terminology committed instruction.
Nice.
Commit number 1.
Yeah.
So what people understand.
That's an excellent point. Yeah. So if you think of it like a transaction and as a committed transaction, that's an excellent way to think about it. These are the things that actually went through the, roughly speaking, transaction processor that a modern CPU is. Okay. So here is the thing that we're talking about. Is anyone familiar with havoc as an instruction when you're doing various kinds of formal work? Fantastic. So this essentially encodes havoc, where star is havoc. It says, if, I don't know, something's going to happen. Now we have 2 rules with no preconditions at all. One selects E1, the other selects E2. Which one are we going to do? It's non-deterministic. We're going to do one. It doesn't matter. We could do both, theoretically, but then we'd have to have an operational semantics that encoded the idea of failed speculative execution. We'd have to have something that told us how to back that out. So in this simple sense of an operational semantics, this is more havoc than it is speculative execution, but this is how you start writing an operational semantics that accounts for speculative execution. So that's non-determinism in a sequential setting. Yes?
So why do you use an asterisk there and not E3 or something?
It's absolutely fine to use any other expression there. That's fine. In some sense, if you do that, then you're starting to conflict with this expression, right? Because we're using a normal form, we don't allow complex expressions in trivial spaces. We want to let bind them. So we don't want to interfere with the expression that is intended to select the correct result. But you're right, star is just a in some sense, it's how Havoc is usually written when you're doing formal verification stuff. So we could choose something else. It could be empty. It could be a little box. It could be pretty much anything. OK, so loops. All right. Anyone want to talk through this loop? Anyone want to have a go? You've seen conditional, so it can't be that bad. All right, I'll have it go. So we're going to do while x e. OK? So as long as x holds true, we're going to run e. Now, we're going to do that in a pretty straightforward way. This is the same thing that we had from the version of the conditional that selected the first branch, right? X has to exist, and it has to be non-zero. But when we rewrite it, we're going to use our sequence operator. So if x is non-zero, we're going to execute e, and then we're going to, in some sense, reschedule while x e. This is one of the advantages of using a normal form versus SSA. So are people familiar with single static assignment, SSA? OK, quite a few. Excellent. So in SSA, you'd end up encoding phi nodes and going through all kinds of stuff about precursors and all this stuff. In a normal form, we get to rebind x. So we get to express much more simply that we're going to check the value of x again, because we're allowed to write to it in some sense. That doesn't mean you should be using a normal form when you're writing a compiler. Please don't do that. But in an operational semantics, it's quite nice. OK. How about that one?
Yeah. Well, the problem with this one is there's probably a statement after the while loop, so we have to execute that one.
There we go. This tells us how to do that. So this is why we have this second rule that's about termination on a value when we have a pair of statements. If there is an expression after the while loop, then the way that we arrived at the while loop is through this. And in this particular case, that's why 0 is returned as the value here. It's not that there's a following expression. It's not that there's a useful result. But we need to proceed to the next expression. Yeah.
I mean, couldn't we just use, a zero sign example or something like void to maybe get, a lack of value?
Doesn't that work?
I mean, 0 could be useful.
I agree. 0 is a lovely number. It's useful for all kinds of things. I'm very pleased with 0. But this does exactly what you want it to do. So in an operational semantics, as soon as you start introducing new concepts into your operational semantics that are not critical to the execution of the abstract machine, then you're creating a more complicated semantics that is going to be much more complicated to reason about. And little warts like that add up very, very quickly. And so being able to say it's an expression or a value, we're done, and saying literally actually here, we could have any number there. It doesn't matter. The only thing that we need is something that is not an expression. That's all we need. So 5. 5 would be a lovely number there. Work just fine. All right. So that's a simple, yeah, sorry.
Why encode a specific value here instead of just like any v is fine?
If we were going to talk about any v, then we'd have to talk about an operational semantics that selects such a v, right? And we would have to start introducing concepts like there exists some v that we're going to plug in. And we can do that, but again, it creates a more complicated semantics. And we just want to make it as simple as possible and keep the complexity as small as possible. Yeah?
So I understand that we don't want to muddy up this operational semantics with that, but in a real language where you would want to be able to use the value that results from this?
What value results from this? But wait a minute, no. I mean, does this language treat while as an expression that returns a value? It doesn't. And the reason is that it's a normal form. So a normal form doesn't really treat anything except explicit assignment to a let-bound variable, a stack variable, as something that returns a result. That doesn't mean that there aren't languages that explicitly use while as an expression. I wrote one. It's a terrible idea, but I did do it. Yeah?
So right now we don't have function call, but
That's right.
if you had function call, one could imagine that this would be the return value.
Yeah, exactly. Now, when you get into that in a normal form, often what you want to do is say that in order to save the value of a function call, you're going to have to explicitly express it as x equals f of whatever. And then it has to be f of let-bound variables, not expressions, which means you have to execute all your expressions that are arguments before you invoke the function, right? So if you're going to do this style, then you're throwing away lazy execution, but of course then you can also start talking about those things produce closures. Those closures will be executed on need. Those closures can then express lazy evaluation inside the closure, and you can actually get, roughly speaking, the whole thing. Yeah?
But if you do this, then you need an explicit return for the function if you don't, like, if you had function calls, and the function had a body that was just a while loop, you would get the value when you assign to the result of the function call.
So you don't necessarily need an explicit return. There are lots of different ways to encode it. You can say that you require a return statement. You can say that the final value that the function produces is the final thing, in which case you would simply take whatever you wanted that was bound to your value, some y, and insert that as the last instruction after the while.
Yeah, I mean, this would be a way to get the resulting value from the while into a variable.
So again, because we're using a normal form, and there are lots of different approaches to this, please don't think this is the only one. We're going to take whatever is in E, and that's a non-trivial expression. So we're not allowed to use the result. We have to bind it to something in order to use it. So we'll bind it to some invented variable.
I mean, if the while, it doesn't really matter. If the while is the body of a function, and you can assign a variable to the result of the function call, then on the upper stack frame, the variable that would be assigned to the function call would be the result of the while loop, like the zero, whatever.
If it was the only thing, right? If you didn't want to return a result. Yeah.
So far, we also don't have any notion of what it means for a program to terminate successfully, right? I mean, we can say we are done evaluating it once we have no other rules that we could apply, but that could also mean that the expression is invalid.
Right. So actually, funnily enough, we do. It's an excellent point, but we do. And it's actually the second rule. That selects E2 such that eventually, any of these rules that is not followed by an additional expression that evaluates to a value rather than an expression terminates execution. Yeah?
You can't evaluate the program with a single expression?
You could evaluate a program with a single expression. It could be any of these. For example, you could evaluate the program x equals v. Yeah. And you'd say x equals 7. It would say, fantastic, 7, and I'm done with execution. All right, so that is a very simple sequential semantics. And as you all have already started pointing out, this doesn't really give you a programming language. It just gives you the start of how you execute inside a frame. We can add function calls, and now we turn the frame into a stack of frames. That's super good. And frankly, not that hard. That's a really easy thing to add to a sequential semantics. We can add a heap and allocation on the heap. That may sound hard, but actually that's not that hard either. Spatial and temporal memory safety is hard, but just having a heap that you're allowed to get fresh addresses on and write all over is pretty easy to express. We can add manual memory management, reference counting, non-deterministic garbage collectors. Okay, that's all more difficult, but relatively easy to express in this kind of sequential operational semantics. We can extend values to include addresses on the heap, add structured data with fields. We can extend that structured data with methods, dynamic dispatch, dynamic type information. Ta-da, we have, roughly speaking, a single-threaded object-oriented language. And it turns out this is, roughly speaking, the traditional single-threaded object-oriented semantics that people tend to target if they don't imagine that they're inventing a semantics. This roughly is what people target. Now, there's some stuff that people go, oh, but you can't possibly express what I want to do there. How would you possibly express tail call optimization? Well, you don't. Tail call optimization is exactly that. It's an optimization. Now, there are machines that explicitly encode tail call optimization as an operator. And that's extremely useful when you're writing an interpreter. But you don't have to bind your abstract machine to require that that happens. Now, you can, and sometimes that's useful too, because you want to prove that you're not going to blow out your stack, and therefore you want an operational semantics that allows you to show that you're not going to blow out your stack. So that's useful, but you don't have to. Yeah?
So if you have GC directly in your semantics. You might want tail call optimization as well in the semantics, because that will affect stuff that is reachable from the stack.
Very much so, yes, because you drastically reduce the number of routes once you've got tail call optimization. Yeah, and making sure that your actual code gen or interpreter, or however you're choosing to do execution, follows the rules that the programmer expects is a good reason to go ahead and encode that stuff explicitly in the operational semantics. That's an excellent point. Pattern matching, high order functions, lazy evaluation, I accidentally touched on that just a bit before. You can actually express that all in terms of a simple sequential semantics, right? It turns out as soon as you can code an object with a single apply function, roughly speaking, is a closure, or in fact, any higher order function, and that's it. It's an object with a single entry point. At the operational semantics level, that's really obvious. At the programming language level, not so much. So, multiple dispatch, logic programming, exception handling, strangely not that hard to encode. Roughly, in some sense, some of the earliest expressions of exception handling just encoded it as a different way to return on the stack and pop frames. It gets a little bit more complicated when you start talking about what one ought to do as one unwinds, right? So C++ exception handling, you definitely want to add a bunch of very specific semantics to your abstract machine about what the hell that thing does. But the general concept of exception handling, where it can sequentially unwind, is really easy to talk about. A little bit more interesting is non-local returns. Is anyone familiar with non-local returns from Smalltalk and stuff? Super fun and powerful feature. It basically lets you say, I'm going to have a return in some frame, but I'm not returning from that frame. I'm actually returning from the source of the block in some sense, in the Smalltalk sense. Often that gets encoded on actual interpreters as some form of exception handling, which is very sad because it's much more powerful than that. But anyway, Smalltalk bias. So that's more complex sequential semantics. System level sequential semantics, you start getting into some hairy stuff. So SIMD instructions, roughly speaking, vectorizations. Everyone's comfortable with SIMD, single instruction, multiple data? Okay, good. Basically, I have, roughly speaking, a vector, and I want to do a math operation over the vector all at once, or a couple of vectors. There's a tendency to say, oh, that's really easy. I'll just add this SIMD instruction and everything should be fine. I think Ben might agree that that's not as straightforward as people think, that it has some significant impact on your abstract machine. You start talking about additional registers, different kinds of registers. Are you allowed to pack this thing in? It's expressible, just takes a little fiddly time and effort, and make sure that you hit the different platforms you want to target. Because again, it's an abstract machine. You're not saying, oh, it must be like an x86. You're saying, I want to do vectorization on a number of targets, and that's why it's more fiddly. Non-strict floating point maths, that's not that bad, actually. It tends to be just a different set of operators that you do over stuff, where you're going to ignore IEEE 754R and go ahead and do something fast instead. Interrupt handling, dynamic linkage, okay. Now it gets hard. It gets really platform specific about what you're doing. Yeah?
I mean, the question is, how would you implement the sequential, how do you implement like interrupts or, unit signals on the man, for an abstract machine?
Roughly speaking, it's about asynchronicity. So interrupt handlers are not parallel, but they are asynchronous. So they are a certain kind of concurrent. They're delivered to some unit of execution, traditionally on Unix, some thread, right? That doesn't have to be. There's lots of different ways you can talk about that abstract machine. There's lots of different ways you can say, oh, look, the fact that on Unix it tends to be some function invocation where you've got a poisoned stack where you can do this very small number of things, that's not how you have to express it. You could say that, in fact, it asynchronously schedules some piece of work, and your entire abstract machine is built around asynchronous scheduling. And now you no longer have to talk about it in terms of those absolute bottom-end concrete details. And you can turn interrupt handling into a much more tractable problem by doing exactly that, right? So that's when we get into your parallel semantics, but I'll get to that in a second. Right, so parallel semantics. This thing that we've been talking about so far is often referred to as a random access machine. And what we're talking about now is what's often called a parallel random access machine. And It's not that different from a Turing machine. It tends to talk about things a little bit differently in the sense that there's some address space, it's a limited address space. There's more about resource constraints in this kind of a model, but it's not that different. And if you take this and you add multiple stacks, i.e. threads, where a thread, roughly speaking, is a stack and some expression, roughly speaking, and you non-deterministically select which stack to execute next, you roughly have a parallel semantics. It might not be a great one, but you have one. You keep a single shared heap. You can start adding atomic operations with their own inference rules that can do things like fetch and add as a single atomic operation, i.e. a single inference rule. Hey, you've expressed your atomic operations. That's great. Super good. You can model concurrency with non-determinism, and that gets you parallelism. Super cool. Yeah?
Of course, that only does, sequential consistency.
Yeah, exactly. It only does sequential consistency. That's absolutely right. And you have to talk about much more detailed stuff to get past that. So first, is everyone familiar with this diagram? Joe Armstrong, we miss him, drew this some time ago. And this is the coffee machine explanation of concurrency versus parallelism, where concurrency is 2 queues, 1 coffee machine. Parallelism is 2 queues, 2 coffee machines. Does that make sense? All right, fantastic. So with a single coffee machine, the queues are actually, people get confused and they think, oh, well, Joe did all the work on Erlang. These must be message queues. No, these are instruction streams. And the single coffee machine is the thing that is going to execute instructions in your instruction stream. And what you're saying is it's concurrent. These are totally logically separate instruction streams, but something is going to select and execute from some stream non-deterministically. Parallelism is we've got 2 totally separate coffee machines. It's good. Go much faster. Don't change queues, especially not if you're an instruction. Okay. Is that good? Then let's start talking about it. So now we can say, imagine we have some heap, and then roughly speaking, it's a map of address to object. I don't mean that in the object orientation sense, but in the sense of an allocation object. I'm not going to talk about the nature of structured data inside those allocation objects, but you can imagine that it exists. We've extended values. Now they might be integers, they might be addresses. Now we have stacks that are some sequence of frames. Now we have a thread that's a stack and an expression. Sound good? Anything problematic? All right. Who wants to have a go at what that does? You have Chi, right? Chi's a heap. Now we have some stack, and the dot just means, in some sense, sequence append. So we have a stack and some frame and an expression. So what this is this is a new shape. This is a shape in the presence of a stack and in the presence of a heap. And we're going to say that for any given expression, what we're going to get out the other side is some new heap, some new stack and frame, and that should have a prime on it because it doesn't have to be the same expression, but either an expression or a value out the other side. That's a new shape. Okay. Yeah.
Is there any particular reason you put a dot between the Greek letters?
Yeah, so this is about being able to say that we're going to select on that frame, that that's the frame that we're actually executing over. So when we start writing the precondition for any of these inference rules, we're going to want to be able to talk about the frame we're in. There's other ways to do it. We can start decomposing it. We can say for any given sigma, we're going to decompose that into some other sigma prime that has some frame after it. That's a perfectly fine way to write it. And in fact, in this particular case, as a shape would be a better way to write it, because this doesn't let you throw anything away off your stack. And we want to be able to do that when we return from a function call. Yeah, it's exactly what it is. Everything's Lisp once you start running it.
So the thing between the first 2 commas is a list, and you just name the thing that's at the head of the list separately from the rest.
Right.
So
First and rest.
I mean, it's just a different variable.
It's just
we have a rule that changes the sigma.
Right.
Moving it over, popping it. Should not be a sigma prime strip.
It really, no, and even more so, I would say that this probably should elide that in here and just say sigma and sigma prime and not mention first versus rest. Even though you're going to need it when you write the actual rules, as a shape, it's nicer to write sigma and sigma prime. Yeah. Yeah, more bike shedding, fundamentally good, as Joe taught us. That was the lesson of his talk. it's not a set because it's a sequence of frames, right? So this is definitely not a set of frames, because I don't know what that means. I'm sorry? Definitely a sequence. Please don't reorder my frames. Call CC. Was that out loud? Damn. Okay, so then we have this really simple set of stuff that explains parallel execution. This is all natural based on everything we've covered, right? No? Anyone want to have a try at this? 2 separate rules, you can decompose them individually. Sorry? Theta is some thread that is a pair of a stack and an expression.
You have not explained the overbar notation.
My apologies, I have not. The overbar annotation means a sequence, arbitrary sequence, but definitely a sequence and not a set.
And you really have to go Greek. I find that's not helpful. Just use alphabetic letters. It's so much.
So concise.
Which professor? It's more it looks fancy.
Look, the thing through the middle, that's a racing stripe. Makes it go much faster. Jeez. Right, okay, so. Yeah, that's the slow part. That's the part that has to run through the slow path, so. All right, good. So this is non-deterministically selecting the thread that we're going to execute. And the reason we have 2 rules is because some threads are done and some threads aren't done. That's why we have 2 rules. The one on the top is threads that aren't done yet, and one on the bottom is a thread that is terminated. And we're reusing this ability to return a value rather than an expression to get that. And specifically what we're doing here is we're saying, okay, we have a heap. We have some sequence of threads, possibly empty, and a thread, and some other sequence of threads, possibly empty. Given that, we're going to take this particular thread, which at this point now could be any thread, right? Because we have a sequence of threads, but we're allowing an unbounded list of them on either side, so this can be any thread. And we're going to do one of the sequential small steps, and then we're going to put it back in with the new sigma prime and expression prime and the modified heap, and non-deterministically select the next thing to do. Similarly, if the thing does not return an expression, then we just don't put it back in the list. That thread is finished. We're done. Okay. Does that make sense? Fantastic. This is basically how you encode a parallel operational semantics. That's pretty fun stuff. But as we talked about briefly before, oh yeah, sorry.
Just to clarify, so how many coffee machines are here?
Sorry.
How many coffee machines are here? So there's only.
This is unbounded coffee machines. Oh, sorry, no, this is unbounded queues. This is a single coffee machine, sorry, yes. Yeah, no, this is definitely a single coffee machine. And the reason Joe wrote that diagram is because he was trying to make it clear to folks that actually the single coffee machine model definitely suffices. You can do absolutely everything with a single coffee machine model and show how parallel execution works. You just have to get your inference rules small enough, because there is something that is atomic about the ordering between these things before they're able to observe each other. So just because they're able to do things simultaneously doesn't mean that observation is simultaneous, right? Okay.
Why do you have a list of threads rather than a set?
That is entirely out of my personal laziness, because I want to be able to describe the thread that I'm taking out of there and then put it back in. It's also fine to encode it as a set and say it's some set of threads unioned with this specific thread. And then I'm going to put back in the set of threads unioned with this modified thread. Absolutely fine. All right, so memory ordering. This is where this gets super, super hard. And this expresses sequential consistency. And so that stuff about observation really makes sense when you're talking about a sequentially consistent semantics, but it really doesn't make sense when you're talking about a relaxed memory model. And you start talking about, okay, can I get more specific inference rules? And the answer is not entirely. Once you start getting more specific inference rules, you start having to talk about what does it mean for something to go in the store buffer? What does it mean for something to get in the load buffer? What does it mean for something to get reordered? How is that observed on a different thread? when we select that other thread of execution, what stores to that heap are visible. And you start encoding heaps in a drastically different way, because of course there's no such thing as a single shared heap. No computer has worked with a single contiguous memory in a very, very long time. We have message passing. That's all we have. We have message passing. That's how we communicate. There's no shared memory, and the hardware guys pretend that there's shared memory and offer us this abstraction because they think that's what we want, and then we get angry at them for doing that because it slows the computer down. It's a wonderful relationship. So, this just flat doesn't work for relaxed memory models. Is it still useful? Yeah, I think so. So, sure, you can start extending it and talking about relaxed memory models, and that's something that I'm really keen on in terms of being able to express a better language for writing runtimes. But that's not the same thing as expressing a good language for writing systems code. And one of the things that we could do, for example, with this kind of thing, is express an operational semantics that has mutation, is parallel, is efficiently implementable, but has no concurrent mutation. And with no concurrent mutation, you no longer need to talk about a relaxed memory model, because all of those observational effects go away. So that's an example of an abstract machine that allows less than the concrete machine. And that's very often what you're looking for. You're trying to omit architectural details because they aren't pertinent. You want to allow fewer operations than the machine is actually fully capable of. So restricting that abstract machine, usually you're doing it to improve reasoning, to improve safety, to improve performance, maybe 2 or 3 of those. But generally, if you're not doing it for at least one of those, ask yourself why. But the implicit C abstract machine that I keep mentioning, that doesn't exist, has this flat undifferentiated address space, and finding out how to restrict that, that's still an active area. Don't get me wrong, the work on the C11 memory model has been fantastic, but this work is not done, right? Yeah.
What do you mean by restricting it?
Sorry?
What do you mean by restricting the abstract machine?
Not everything that the C11 API says is possible is in fact possible, right? There are many things in the C11 API that are effectively meaningless, right? You say, oh, go do this with your C11 atomic operation API, and the hardware won't do anything like that. And there's no hardware that will do anything like that. And in fact, it's not even rational to think about that as an operation. Relaxed memory ordering atomic exchange is one of my favorites for this. If you can tell me what that means, boy, I buy you a beer straight up. Right, so being able to restrict that and talk about stuff that really exists should theoretically help us reason about how C actually works, which would be nice. But if we're going to talk about this thing of removing concurrent mutation, why would we do this? This is just a use case. Just a use case. There are many use cases. But roughly speaking, the safety issues in systems programming are spatial memory safety, temporal memory safety, and data races. And when I say the issues, I mean when you go through the folks that spend a lot of money fighting bugs, between those 3, you're running, roughly speaking, 75% of cases, but consuming more than 75% of the budget, and so we're talking about billions with a B. So it's all about the Benjamins, and this is an interesting possible reason to talk about a operational semantics with no concurrent mutation. So if it isn't necessary for your problem domain, why not take it out? How often do you want to violate spatial memory safety on purpose? Seems unlikely. Yeah?
If you're doing an OS, certainly.
Sorry?
If you're doing an OS, certainly.
I disagree with that, but we can talk about that later. I certainly do not want to violate spatial memory safety in my operating system. If you had said, if you're writing a memory allocator, and there is no such thing as spatial memory safety or temporal memory safety when you're writing a memory allocator, because there is literally no programming language in the world in which writing a memory allocator is well defined, then I would believe you. Have fun writing your memory allocator correctly in C, since C says malloc and free are not, you're not allowed to implement them effectively, right? You're not allowed to examine memory once free has been called. And you know, I'd like to do something with that memory, like free it. Anyway, so There are many approaches to this, right? So why would you get rid of concurrent mutation? There are other things you can do. You can do transactional memory, you can do linear types. This is just a point in the design space. This is about why would you want to go down this route in the first place? But let's say you don't want to do that. So spatial and temporal memory safety are really easy to talk about why, it's pretty easy to say you don't want to do that, other than memory allocated people. Data races is a little bit harder. There are times when you want data races. For example, if you're implementing a scheduler, you're going to want data races. If you're implementing concurrent queues, you're going to want data races. If you're implementing synchronization primitives, you're going to want data races. But those are all things that you could encode in your operational semantics and say that these are not available in your language, but they are in fact primitive to your language. Maybe. So what would we do if we wanted to build a pram without data races? So in the pram model, there's a single shared heap, okay? That's the problem, roughly speaking. We could associate a heap with each thread. That's it. We've eliminated data races. We're done. It's fantastic. Every thread can only read or write its own heap in its own stack. Fantastic. We have a perfect data race-free programming language. We also can't communicate between threads. There's no cross-thread communication once we get rid of that shared heap, because all we had was observing concurrent mutation. That was the only thing we had for communication. So probably that's not what we want to do. We could associate a mailbox with each thread. Mailbox might allow concurrent push, but only allow the associated thread to pop, right? That's a multi-producer single consumer queue. Those are super fun to implement, all kinds of fun MPSC queue designs. And then if the mailbox matches that have to be primitive values, now we have communication and we have perfect data race free, pram, and that's pretty neat. Except that we don't want to communicate values, primitive values. We want to communicate object graphs. We want to send entire object graphs between threads. So that doesn't really work. What could we do? We want object messaging. We could prevent the receiving thread from making progress when we want to send a message. And the sender could, during that period when it prevents the receiver from making progress, copy the entire object graph that represents the message into the receiving thread's heap. And that's safe. And in fact, that's exactly what Erlang does. Has anyone written any Erlang? Anyone? More all y'all got to write more Erlang. This is, roughly speaking, how Erlang works. There's a little bit to do with some large object heap stuff and the usual performance modifications that you end up making when you go down this route. But roughly speaking, that's how actors called processes in Erlang communicate. It's doing exactly that. But it is slow, of course. It's crazy slow. Of course, you don't want to copy that whole thing. We could ensure that the message graph doesn't reach any object that is also reachable by the sending thread. Okay. That's separation logic. That's encoding a limited separation logic into your operational semantics. It's safe and it's super fast if your reachability test is cheap. Is everyone comfortable when I say separation logic? All right. So roughly speaking, this is a sort of approach to a logic, to a sort of a form of formal verification that says, let's talk about, for any subset of the heap, what are the separation properties of that subset versus some other subset relative to the code that's executing. And it's a huge ripe field, bunch of fantastic and interesting research. Matt Parkinson just got a 10-year award for influential paper. It's fun. It's a little hard. Encoding that kind of stuff in an operational semantic says, here's a language in which you don't have to analyze a program to see if it obeys some particular separation logic that you've written down for that program. It says, no, all programs obey this larger separation guarantee. So let's do it. Let's encode a separation logic into the semantics. Fantastic. So we can use a single heap, but we can segment that heap into regions, not necessarily contiguous regions. A region may not be contiguous. And every object belongs to one region and is reachable only from that region. Okay? And then we allow objects in some region R to reference some other region R prime, but not the objects within R prime. Right? Now you have two different kinds of object graph that you're expressing in your program. The object graph that you want to be isolated and the object graph that you don't want to be isolated. Reference count regions And now, a message can only contain a region with a 0 reference count. Well, hey, you've encoded separation logic into your dynamic operational semantics. That's pretty neat. You can move a region from one thread to another, but you can't share it. You've completely prevented concurrent mutation. That's a pretty neat model. But it's not actually all that great. It turns out that's a lot of dynamic operation that you would like to elide, because we have racing stripes on all our Greek letters, and that means we want to go fast. So we can improve that. We can take things out of the dynamic domain and put it into the static domain, start talking about type checkers to enforce these kinds of properties. We can weaken the operational semantics to say we're not going to be specific about how isolation is achieved. And we can start writing predicates to the inference rule that are about reachability rather than the mechanics of reachability. So instead of saying this must be a region and it must have a reference count of 0, we can say I don't care what it is as long as the sending thread can't reach anything that this thing can reach. And now you have a valid operational semantics that can be expressed with a much wider range of actual programming languages. Does that make sense? So enforcing some predicates statically is sort of what I'm leading to in this. This is just a point in the design space. I'm not saying go out and build this language. I'm saying, isn't that interesting that sometimes we've been talking about this dynamic operational semantics all the way through, but in fact, some of your operational semantics can be implemented entirely statically. And that's fun. And whenever you can do it, you do it. So, another possible use case, right? Switching tracks a little bit. Machine learning, the other ML. I assume when I say ML, you all know that I mean the programming language, and thus I will clarify and say machine learning. Specifying all the vector operations you need for efficient machine learning. We've already said that although I say it's simple here, actually it's a little bit of a pain, but it's not that bad. Less simple is scheduling stages in your ML pipeline. Has anyone done any machine learning stuff? Deep neural networks? Fantastic. Reinforcement learning, stuff like this? Okay. So roughly, for everybody else, roughly speaking, it's a big damn graph, and you're going to, roughly speaking, execute your graph this way and get a bunch of information, and then in some sense, you're going to backpropagate through that graph, and you're going to change the weights that you're accumulating. That's like the world's worst explanation of neural networks. But the interesting bit out of this that I'm trying to surface up is that scheduling those things is already hard in terms of getting a fast parallel execution. Getting a fast parallel execution in the presence of constrained memory, where you're actually trying to minimize memory usage, is super interesting. Why would anyone know why you'd want to minimize memory usage on these things? Anyone? No? Video games. There's other reasons too, lots of reasons. Trusted execution environments, enclave programming, stuff like that. But roughly speaking, the video games is one of the huge areas for this. So particularly when you start talking about some of the really interesting new machine learning approaches that are not quite so static as a typical DNN. So a typical DNN is super static, and you go, oh, here are all the temporary matrices. I kind of know how to lay this out. But recursive neural networks, not so much. So one of the things you can do is start talking about the availability of memory in your operational semantics. So when I talked about a heap, I just talked about, it's a heap. It maps addresses to object. What's the big deal? Everything's infinite memory. But in operational semantics that explicitly encodes the idea of resource limits lets you write a programming language that executes with the full knowledge of those resource limits. That's pretty fun and unusual, right? And in this type of approach, I hope, leads you to the idea that this isn't just for general purpose programming languages. Domain-specific languages should have a semantics too, and ideally, a nice, well-defined operational semantics. All right, so pretty much done here. Key takeaways. First, starting with semantics means you're trying to build a language that does something different, not a language that does something better. Right? If you're trying to do something better, that's a valid design goal, go crazy. Usually you're working with an existing semantics and you're trying to improve the user interface to that semantics. That's usually what we mean when we say better. Sometimes we mean faster, but if it's over the same semantics, isn't that just kind of better? Isn't that, in fact, a user interface problem? Because you're saying it's easier for the programmer to express fast code? I think it, roughly speaking, is just a UI issue. So it really is focusing on fundamentally different. You're looking for something that breaks out of a particular mode. Usually we think as in these parallel random access machines. It's not always the case. And you're trying to express a fundamentally different approach to computation for this specific programming language. Detailed explicit small step operation semantics, you know, they're not that hard. I hope you got that from going through this. These inference rules are really easy to read. They're easy to write. Once you've written them down, they're really easy to reason about. There are really nice frameworks that let you even build executable operational semantics where you can start fiddling with it and seeing how it actually runs. There's a bunch of fun tooling for this. And a new semantics can free you from problems that shouldn't exist in your specific problem domain. Right? If you have an abstract machine that doesn't allow operations you don't need, you will have a much better day. Right? So if your problem domain does not require concurrent mutation, just an example, then an abstract machine that does not allow concurrent mutation saves you from, well, in that particular case, roughly 99% of the work that you would otherwise have to do. But that just happens to be a pretty good case. Right. That's it. That's all I got. Yeah.
You just mentioned that there are some tools that can help you building those semantics, those operational semantics. Can you name?
K-framework is a nice place to start. There's a bunch of other stuff out there. Does anyone else have suggestions on operational semantics tools that they want to offer? I tend to reach for the K-framework, so I'm a little behind on other stuff.
Redux?
Yeah, absolutely. Good point. Yeah.
What was that?
Redux. R-E-D-E-X. Anyone else? Yeah.
So how many people start with semantics?
What a fantastic question. Do you want to comment? Yeah, I totally do. I always start with semantics. Right. This is literally two of us. Come on. No, I think there's more and more of this. I think there's some really nice work on Rust with Oxide for operational semantics. I don't know exactly if you would describe that as starting with, but still, good work. Yeah, how often does that happen that the operational semantics comes first? In my crappy opinion, because I'm hugely biased, not often enough. But there are other design goals, right?
Yeah, just a comment. It doesn't come immediately first.
Right.
It comes earlier on in the process. Yeah.
That's a good point.
Okay, so I have my follow-up question.
Yeah.
Which is, how often does it find problems? Because, I mean, obviously, if I define it, it's nice that there's a spec people can read.
Right.
But you can also sometimes find inconsistencies that you may not have noticed.
So for me personally, all the time finds problems. Like constantly is co-design between the type system, the operational semantics, and the actual implementation of the runtime I find to be critical. I don't really personally know how to make progress on a language design without going through that co-design process. Yeah. Or you get, the ad hoc interpreter or compiler that, hey, maybe it does a thing. All right. Anybody else? Okay. Oh wait, we've got one more.
One more question. Referring to the talk yesterday about language design in industry, how often do you actually get to design a new language and to design all this semantics?
I will refer you to the right honorable gentleman on my right. I would like you to note several things about what he talked about. One is that, yes, we should definitely do that less in some sense. Strangely, I think one of my takeaways from his talk is more in some sense. How often? Actually, a lot. We design a lot of languages all the time, perhaps constantly. Sometimes even when we're designing libraries, what we're really doing is designing DSLs, and those DSLs should have an operational semantics. Particularly when we start talking about DSLs to express interesting things. One of my favorite examples is I really wish someone had written down a really nice operational semantics for NumPy before they started. That would have been a great idea. And is that a new programming language? It's a DSL, so in some sense it is, yeah. Right? Anyone?